3 motion for the wrist, 3 motion for the hip, the same for the shoulder, and those motion, the main question, how to produce those motion in robotics. So classically, in mechanics, we have 2 ways to develop those spherical joints. We have what we call serial structure, and we have what we call parallel structure. In serial structure, it's easy to produce motion, but we cannot produce high forces. In parallel structure, it's very easy to produce high forces, but it's very difficult to produce big motion range. The solution that we proposed, we come up with 2 classes of spherical hybrid mechanism. I will show them directly now. So this is our first mechanism proposed for the wrist and the ankle of the robot. It's patent, and we can see that we have one motion, I can use this one. So we have one rotation around the vertical axis, and then we have the 2 other axes here working with a parallel mechanism. Yeah. Those are the first prototype developed in my team. We start like all the day with simulation, and then we go to design, and then we manufacture those parts, and then we test them. Also, we have some demos here, and then the objective is to minimize the mechanical parts, to reduce the cost, and to have a nice motion without having a lot of extra components to manage. So here it's the other proposed solution for the hip and the torso. It's a patent solution. We start by creating this rotation in a serial way. Then we have the 2 pistons there to work together to produce actually this motion and this motion in the sagittal and the frontal plane. Sorry, it should be a video here. Yeah. So now when we answer the question is when we decide which mechanism to use to produce the motion in the human robots, we have to go to answer the question, what's the technology that we have to choose to actuate this robot. From one side, we have the electric actuation, which is easy to use, easy to control, but it gives limited output forces. From the other side, we have the hydraulic actuation, like Boston Dynamic robots. It's easy to produce high forces, smooth motion, but it's high cost, and then it's not energy efficient. So we come up with a proposed solution is to integrate hydraulic activation inside the body of the robot, and then we propose 2 strategy. One is to integrate the hydraulic tubes inside the robots. The other one is to create integrated hydraulic actuator. So as we can see here, the idea is to integrate inside the body of the robot all the hydraulic paths. It's just like having arteries and veins in the human body, so we have the same things in the robot. And then the outcome that we minimize leakage, we increase the compactness of the robot, the social acceptance, and we reduce the assembly time of the robot. But the main difficulty is how to manufacture those mechanical parts. Of course, we have many approaches. The first one, it's classical one. Then we have a metallic 3D printed one, as they use it in Boston Dynamic in USA, in IIT in Italy. But the main negative point that those parts are expensive and heavy. So we come up with this technology, which makes the plastic 3D printed with composite material, and then with this technology we can develop lightweight, robust, and fast and simple process to have those components for the robot. I would like to show those videos. It's kind of demos that we have in our robot. Sorry, I should maybe stop the voice. In the test level, then we can see this arm manipulating 1.5 kilograms. Thank you. Then we have those videos. The same arm is doing some tasks. So this is to show that how it's easy to produce motion with hydraulic actuation. So we can produce high forces. I mean, with this robot, we can take a heavy load, we take it in this vertical position without consuming a lot of energy. Then for the other direction in which we work is to develop integrated electrohydraulic actuator. So the idea is not to have a hydraulic center group in the backpack of the robot, it's to create the hydraulic energy behind the joint. This is what we can see here in this picture. I mean, this actuator, it was designed by my team, and it's one of the smallest in the world in the direction of electrohydraulic actuation. So it's 3.8 kilogram motor, and it can move up to 800 kilogram at the speed of 20 centimeter per second. This solution was patented, and then we use it in electrohydraulic human robot and also in prosthesis. So just a quick plan. So in mechatronics, we start by proposing the principle, then we do the design, we do a proof of concept, and then we develop model. And here we have a mathematical model which is not non-linear, so we need to linearize the model, do some simulation, and we come up with optimization, and this is the last prototype. Then, when we have those mechatronic system expertise, we go to exoskeleton. Why in our team we go to exoskeleton? Actually, we were contacted by an industrial French company. The owner of this company, he has his own daughter. She has a spinal cord injury. She is 13 years old, and she wants to walk again. And then when we discuss with this young lady, we asked, what do you want exactly? She said, I want to go to toilet alone. I mean, and this was for me, it's really emotional. So we start working in this exoskeleton, and the idea is to develop a simple, easy to use exoskeleton. So this is why we choose 4 active exoskeleton with 4 active degrees of freedom. So in the hip, in the knee, and then passive exoskeleton in the ankle, and then this exoskeleton work with big keys. So we don't manage the equilibrium of the person. And this choice was justified by the idea that we want to use it quickly. So this is the exoskeleton that we propose. I mean, I have some picture here that was lost. Sorry. So actually here we are using, I mean, I have some picture to the right, but it's not appearing. So we use electro actuation. So we have a DC motor, BLDC motor with the gearbox. We have sensor, we have force sensor control, electronic control inside. And then we can, as this child is 13 years old, then we have to change the distance between the knee and the hip when the child is grow up. At this picture, I'm presenting the control that we use to control this exoskeleton. So we are proposing here our own electronics and our own custom-made and distributed control in the system. We use ROS from the master level, in which we have it's kind of high-level control, and then in the slave level we have the low-level control. With BID and so on. So this solution gives us the possibility to have high reliability, scalability, and modulability, and we reduce the communication between the master and the slave, and we come up with low latency, which is very useful when you have a very high speed answer. So those are our electronics. Then I will show some videos here. So one of the difficulties that we have in France, that the rules to test in the human they are very difficult. So we have a lot of rules and a lot of conditions to be able to control in the guy. So then recently, during the last year, I hired one colleague in my team, so Dr. Hong Su. And the objective was to develop a new prototype of this exoskeleton. We can see in here. So I have to. So once again, we are using the same technology of having one motion in the hip, active one motion in the knee, and then passive motion in the ankle. And then we use rows to control the system, and then we have some kind of sensor between the foot and the ground to detect the distribution of the force under the foot.
Okay.
Then I would like to go to another aspect. So when we start working with this exoskeleton for this young lady, we start by saying why we don't order an existing exoskeleton, and we find that there is no exoskeleton for teenagers. So exoskeleton, we have exoskeleton for children, and then we have exoskeleton for adults, but not for teenagers. And at this level, I start looking more about this subject, and then we start by having some information, actually going back to some worldwide statistic based in UN and UNESCO information. We have more than 220 million persons under 24 years suffering from type of motor disability. Of course, all kind disability mixed together. 80% of them don't get a job when they arrive to the adulthood, and then 80% of them they are living in developed country, and 90% of those children, I mean, they don't go to school. And then we understand that we are facing a iceberg problem, and then those young users, they are subject to rejection, isolation, because we have this problem. And then the idea that when they move from childhood to maturity, they are suffering from kind of non-integration to the society, more dependent to the family member, and less contribution to the society, and they don't enjoy correctly their life. Of course, the youth solution is the wheelchair. We use wheelchair. It solves the mobility problem nicely, but I mean, in the same times, we create problem related to, I mean, especially when we talk about teenager, and they are characterized by rapid physical growth. So then we create some problem to bladder and spinal curvature, because they are not able to stand and to move. So, and then we have those problems, and this are the main negative point for the wheelchair. And then we have some psychological problem. We noticed that teenagers that used to use wheelchair, they may develop his identity. So it's a kind of body awareness, including the wheelchair. They will feel that the wheelchair is part of their own body. And then when they arrive to the adult level, they refuse to use exoskeleton. They want to stay with wheelchair. So this is why we try to propose assistive devices that can grow up with teenagers. And actually, this is the problem. I mean, once again, we have solution for children, and then we have children for adults. The main company, the main supplier for exoskeleton, if we ask them, they have like female exoskeleton, male exoskeletons, large, small, medium, but we don't have a solution that grow up with the user. So it's a mechatronics problem. So we need to develop exoskeleton and prostheses that can grow up with the user. And of course, the main difficulties while developing those actuators, if you ask me to develop an exoskeleton that can be used when the user is 12 years old, and in the same time to be used when the user is adult, I will take the worst case, and then I will put electric motors able to move the system when the user is adult. But the idea that when the user is child, so we are putting a very big motor at this level. So unless we change the mechatronic solution, we don't have up to now we don't have a mechatronic solution that can grow up with the guys. And at this level, the electrohydro actuation, the actuator that I proposed before, can do the job because it's scalable. With a very small actuator, we can produce high amount of forces. We don't need to change this actuator all the time. Usually what I know, and while discussing with our colleagues in hospital in France, they use 3D printer for teenager user to do kind of mold, and they change it each 6 months and sometimes each 3 months, which is a lot of investigation to do at the level of time and budget. So here at this picture, I would like to show all the nearly all the existing exoskeleton, and we can find that all those exoskeleton it's developed for freezing physical characteristic. So it's for adults. We can adapt a little bit the tie, the dimension, but it's not growing up with the user. This is why the main need is to develop lightweight, scalable exoskeleton for teenagers. And when we talk about scalable, this means that the exoskeleton should change physically the characteristic in a continuous way. And when we talk about characteristics, so we mean the dimension, of course, the force, the performance, the stiffness. So we don't know if the user at the level of the teenagers, like 14 years, he is working in the same way like after 2 years. And when we add the exoskeleton, we should ask the question, are we correcting the things in a nice way, or are we doing kind of perturbation to the system? So it's still a big question about how to develop a lightweight, scalable exoskeleton for teenagers. Then, because I'm originally from Syria, so I'm interested about what's happening around the Mediterranean Sea, and then we can find two phenomena. So in Europe, I mean, we need, based on the statistic, we have like 12 million persons with dysfunctional limbs. So mainly we need exoskeleton, and mainly the user is elderly people. But on the other hand, in the south of the Mediterranean Sea, and even, I mean, in this study we go up to Afghanistan and even Yemen, we have 23 million persons that need limbs. And what was difficult, because this study with those statistics, it's very hard to have this information. I mean, we interact between journals information, some website, and so on. We find that it's dramatically increased after 2011. So in Libya, we go from 0.1 to 0.4. In Syria, from 0.2 million, so up to nearly 1 million. And then in Egypt, it's a big problem. I hope there's not a lot of colleagues coming from Egypt. I mean, they have a problem with from the Second World War, and then they receive a kind of subvention to be held, and then it's a big problem. They don't want to clean this area, but they live with it. And then the mainly victim is women and children. This is why we need to develop a suitable legged prosthesis. It should be available to everyone. It should be scalable, because we are talking about a teenager, and it should be comfortable. And if we have this picture, someone coming from Africa, the only thing that can he hope is to draw his legs in the ground. And then if we go to the market and we scan all the existing prostheses, I don't know if you can see in green the price of those prostheses. We are going from $25 up to $200. So recently, a few weeks ago, I was in workshop with Gaza, and unfortunately, during the last 2 years, they have a lot of increase in this need, and we cannot imagine that someone in Gaza can investigate like 100 kilo euro to have an prosthesis. And the problem is that even in France, I mean, we have some social support, and then the government offer these tools. I meet some users, they do a lot of efforts to receive the prosthesis, and then after a few weeks, few months, they put the prosthesis behind, and then they go back to wheelchair. And the main reason that they used to use the exoskeleton, they used to use the wheelchair during the teenagers. So it's a key period. If the user have the habit to use the wheelchair during this period, it will be very difficult after that, when he is adult, to bring him back to real life, even with prosthesis or exoskeleton. So those exoskeletons, they are not they are very expensive. This is the main reason, and then they are not scalable. So they are not adapted for teenagers. This means that if we propose those solutions for teenagers, we need to change the solution each 2 years. And usually prostheses need a few months to be adapted for user. This means that every 2 years we need to spend 3 months to investigate for another prosthesis, and it's very expensive and it's very time consuming.
2 minutes, Professor Faya. 2 minutes. 2 minutes.
This is the most important things. So our idea is to propose what you see here. It's the first maquette of the prototype that I proposed. I was planning to bring it with me, but it was a little bit difficult. So it's a low-cost, scalable, active leg prosthesis. It's available one, affordable one. The main part to create the motion, it's with the electrohydraulic actuator that I proposed before. Then the accessories, it's done from 3D printed carbon fiber. So our objective is to create a kind of foundation. I discussed with many authorities in France and in Monaco, and we need to create connection around all the Mediterranean Sea to work together, because one of the parts is to have some prostheses that not expensive, and the other difficulty is to have staff, medical staff locally that has the capability to use those prostheses. And then finally, I would like to thank my team. So usually we are between 10 and 15 persons, research engineers, PhD student, and postdoc. Thank you. Anytime.
Thank you very much, Professor Fayyad, for the presentation of your interesting research. We have time for maybe 2-3 questions. So, any questions?
Thank you very much, Dr. Samer, for this talk. I just have a question regarding the exoskeletal, especially when you talk about the pediatric or the children and the size of it, and even when you talk about the 3 degrees of freedom for the different joints of the lower limb. I just want to ask, usually it's being used for neuromuscular disorder or disabilities, let's say. Is it applicable to use it also for musculoskeletal disabilities or not?
It's possible, but we have some problem that for this patient they start unintentionally move the body, and then this means that control of the exoskeleton should detect the intention of the human. To answer, we need to add one more layer for the control to detect the intention of the user.
Okay. Thank you very much, Doc. Thank you.
Thank you very much. Any other questions?
Thank you, Professor Samer, for the very nice and informative talk. So actually, since I have a control background, so I was attracted by the use of PID controller. So I'm curious to know how this controller will react in the presence of external disturbance, for example, obstacle.
Actually, I would like to mention one point that we start with the BID, then we go to adaptive BID, and then recently we use the sliding mode. As I mentioned, we are funded by this company, and as now he is my friend. He make me meet his daughter. So then the question is, do I have to do a nice control, then I spend a lot of effort, or do I have to give something work at even 50% of the time? And when we are face of the user, it's not research. It's not a completely research project. We don't have the time to develop whatever we want. This is why we start with BID. We adaptive twinly to overcome the friction and so on, and then we go to adaptive BID to standing mode.
Okay. Thank you. Thank you.
Thank you very much. We have time for one more questions, maybe. Any other questions? No questions? Okay. Thank you very much.
Thank you.
Thank you very much.
Thank you very much.
So let's invite the next keynote speaker of today's session, Dr. Latifa Alenzi, please. The title of the talk of Professor Alenzi is Risk of Sarcopenia among Community Dwelling Older Adults in Kuwait. Let me briefly introduce the speaker. So, Dr. Alenzi is an assistant professor in the physical therapy department at Kuwait University with over 18 years of clinical experience. She specializes in musculoskeletal and geriatric rehabilitation and holds a subspecialty in cognitive behavioral therapy. She earned her PhD in physical therapy from the University of Sheffield and an MS from Sheffield Hallam University, UK. She leads multiple research projects, including randomized controlled trials and machine learning application with publication in leading Q1 journals. Please, Dr. Alenzi.
بسم الله الرحمن الرحيم والصلاة والسلام على سيدنا محمد خاتم الأنبياء والمرسلين. السلام عليكم ورحمة الله وبركاته. Good afternoon, everyone. Today I present for you the results of my recent study, which is the risk of sarcopenia among the community dwelling or the older adults, which is population-based study. It's important, as we're talking about community dwelling older adults, it's important to start with the statistics and some of the totals of those population in Kuwait. So population age 65 years old and above of Kuwait was 2.8% in 2011. The Kuwait's older adults population is increasing or growing, and it's expected to reach 10 to 15% by 2030. And dramatically it will increase to 17 or 18% by 2050. Considering this increasing number of those population in Kuwait will increase the demand for geriatric care, rehabilitation and physiotherapy services, and this will place a strain or a stress on the healthcare system in Kuwait for the future years or the coming years. So here is some of the totals of the Kuwaiti population, Kuwaiti and non-Kuwaiti population who are aged 65 and above. And this is the recent update in the Public Authority for Civil Information, which is the Statistical Services System. It's really one of the nice systems websites, and this is from the current one, or the current last update, which is June 2025. Really the system is friendly, nice. You can search for statistics or total of the population according to the age, gender, according to the governance, whatever you want, you can search for it, and it's really nice. So the number of total Kuwaitis is 81,945, and non-Kuwaiti is 65,200. And we can see here this is a pie chart that divided the population by nationality. Here is the Kuwaiti and the non-Kuwaiti, which is approximately near, and the percentage of the total population reach 3%. So what is sarcopenia? Do you have any idea about sarcopenia before? Do you hear this syndrome before? Okay, nice. So the sarcopenia is one of the age-related condition, let's say, or syndrome, progressive syndromes that marked by three things: the loss of muscle mass, strength, and the physical performance. And sarcopenia is increasing the risk of fall, the fractures, the hospitalization, and the functional decline, as well as depression in older adults. So according to the Asian Working Group for Sarcopenia 2019, they used the muscle strength, physical performance, and muscle mass assessment for diagnosis of sarcopenia. So sarcopenia is not merely a natural consequences of aging. It's actually a clinical recognized syndromes with serious consequences and implication in the healthcare systems and the caregivers. So it's recognized as a major geriatric concerns. So early detection will enable the healthcare provider to provide a tailored, individualized treatment for those older adults to improve their quality of life and their treatment outcome. So let's talk a little bit about the global impact of sarcopenia. Sarcopenia affects 10 to 27% of older adults globally and increase the health care burden and societal costs. For example, in US, the sarcopenia account for about $18.5 billion in healthcare costs, highlight its financial impact, and this number is not as small as you can recognize. So beyond the financial cost, sarcopenia also contribute to increase the mortality and morbidity, disability, and placing a huge demand on the healthcare system and caregivers. So screening tool like SARC-F it was the primary tool that we use in our study, together with the physical test, are vital for early detection of sarcopenia to enable timely intervention. So moving from global to Kuwait, while the international guidelines such as the Asian Working Group for Sarcopenia facilitate the research or the sarcopenia research across the Asia, there is still a notable limited or lack of research within the Arabic countries and with no specific research in the Kuwaiti population. This gap in research is concerning given the unique cultural and environmental factors of our countries that will elevate the risk of sarcopenia in the region. For example, as you know, the Kuwait has experienced in the last 10 years, let's say, a rapid change in the socio-economic that increasingly lead to sedentary lifestyle, and no one can deny that. So the physical inactivity also in our countries is combined by the environmental challenges, such as, for example, the extreme heat that discourage the outdoor activities. Also, the cultural norms, for example, for the ladies or the women, that prevent them, for example, from the sun exposure, which contribute potentially to the deficiency of vitamin D. These factors, together with unhealthy diet, together with unemphasized structured exercise, create a high-risk environment for sarcopenia among older adults in Kuwait. So, therefore, our aim of our study was to estimate the sarcopenia risk in community-dwelling older adults in Kuwait, and also to explore the interaction between the sarcopenia risk and the determinants of frailty, which is the mobility, strength, independence, and falls risk. So, as we are now talking about the sustainabilities and also as the United Nations with us here and emphasizing the sustainable developmental goals, our study is strongly aligned with Kuwait Vision and the United Nations Sustainable Developmental Goals. The Kuwait Vision 2035 heavily emphasizes improving healthcare quality and longevity as a core strong pillar aiming to develop a more efficient, sustainable healthcare system through massive investment in the infrastructures. As you know, there is a lot of new hospitals. Also through the digital transformation, the AI and the digital health record, as well as the specialized centers that looking to enhance the health outcomes and elevate the citizens' quality of life, positioning the Kuwait as a regional health leader. In regard to the Sustainable Developmental Goals by United Nations, also this study is strongly aligned with particularly the Sustainable Developmental Goal number 3, which is the good health and well-being. This is because our study addressed a critical aspect of the health aging, preventing and management of serious conditions like the sarcopenia among older adults in Kuwait. So now we will talk about overview of the methods and the results. So we have our study, we use a cross-sectional study. We aim to evaluate the risk of sarcopenia. Our participants were community dwelling older adults, age 65 and above, able to independently ambulate either with or without assistive devices. And those who are in, we follow exclusion criteria, for example, for participants with who are having a condition associated with cachexia, such as the cancer or the heart failure, as well as the severe cognitive comprehension problem or impairment, because we need them to comprehend nicely with the study material. We use multiple validated outcomes measures in our study. First of all, as we said, the SARC-F questionnaire, which is used to identify people at risk of sarcopenia. And we also use functional and frailty skills like the physical self-maintenance scale, which assesses the independence in daily activities. We use the short fall efficacy international to evaluate the fear of falling, and the frailty status. Also, we perform in-person physical performance test, which is including the 4-meter gait speed, time up and go, 5 sit to stand, as well as the hand grip to check for the strength of upper and lower limb for those participants. This is the SARC-F, which is an easy questionnaire or tool that's a screen for sarcopenia, include 5 components: strength, walking assistance, getting up from a chair, climbing stairs, and fall. If the score is equal 4 or more, the people recognized or classified as having risk of sarcopenia, and if it's below 4, they are not at risk of sarcopenia. By the way, this questionnaire is origin just in English. We don't have an Arabic version of it. But we, and almost all the questionnaire we used was translated. We used the Arabic version of it because it's validated, except for the SARC-F, because we didn't find an Arabic version. And I'd like to share with you, and I'm excited to share with you, that we are in the last stage of validated it in Arabic in another study. So this, the procedure that we follow, the convenient sampling was used with recruitment from flyers, social media, and word of mouth to engage the participant. Structured sessions, each sessions for one person or for one older adult, it took us 45 to 60 minutes. As you know, the elderly, they have a slow mobility, and it takes us almost 1 hour to complete all these measurements. We do the questionnaires, the standardized performance of the test by trained physiotherapists who talk Arabic and English, who is bilingual, to give participants time to understand the questionnaire and ask questions. The confidentiality and informed consent were prioritized to ensure the ethical standards through the study process. And as you know, this study already is endorsed for publication in Q1, so already we have the ethics for it from the Kuwait University. For the statistical analysis, we use the descriptive statistics to summarize the participants' data. We use the participants were classified or grouped in two groups. So those at risk of sarcopenia and those at non-risk of sarcopenia for the purpose of comparative analysis. We use chi-square test ANOVA for the comparative analysis, and we use the logistic regression for the to see the predictor of sarcopenia. So as an overview of the key findings, the study included 92 older adults. 32 of them were at risk of sarcopenia based on SARC-F scores. Nearly half of the participants were with a category of a pre-frail. 18.5% were having frailty with common limitation in grip strength and mobility. Sarcopenia risk was interestingly linked to gender, age, education, health status, and chronic conditions. This is a brief about the demographic. As we said, we have 92 participants. Most of them were male, to be honest, and we acknowledge that in our limitation in the study. We have fruitful age groups in our studies. We have 60s, 70s, and 80s. Most of the participants were having more than 3 condition or chronic condition. Almost 40% of them having more than 3 conditions. In regard to the distribution of the risk and the functional performance, as we said, that 31% are at risk of sarcopenia, and 68 of the participants were not at the risk. In regard to the frailty, almost 18%, 18.5 having frailty, and those with reduced hand grip, which means they have reduced upper limb strength, almost half of the participants, which is the percentage is 53.3. Also, the 82% having abnormality in 5 sit-to-stand. They took longer time to complete the 5 sit-to-stands, which means they have lower limb strength is reduced. Okay. Also, for the tug, they took a long time to coordinate during the time up and go. Time up and go is it's designed to assist the coordination and the mobility. So they will stand up from a chair, they will walk 3 meters, and they will turn and return back and sit to the chair. And there is specific time to complete it. If they are taking longer time and they are slower to do it, or if they are failed to return, this means they're having an issue with the mobility and maybe the fall as well. So almost also for the tug, almost half of the participants were abnormal. Also for the gait speed, they are having slow gait speeds, 41% of them. And regarding to the fear of fall, we have 3 categories according to the scales. So we can classify them as having no concern about the fear of fall, or having moderate concern, or having great concern. Actually, approximately half of the participants, let's say, having a great concern of fear of falling. In regard to the dependence or independence, regarding the physical performance, we have 42% having ADL dependence. What do you think about the findings, guys? It's really disappointing regarding our elderly population. Almost of them having, and this is just a preliminary study. We are aiming for large national study after we finish the Arabic validation tool, and also we didn't use here a muscle mass measurement because of the logistic limitation as we were collecting the data in community, and also due to the budget. This study also was funded by Kuwait University. However, we didn't use the muscle mass, and we acknowledge it as a limitation, and we are aiming in the future to use it. So the key association with the sarcopenia in regard to the gender, female are affected more with the sarcopenia. The older age are susceptible more to sarcopenia, especially those in 17s. Also who have lower educational level, and this is what's interesting for us, are having increased vulnerability to sarcopenia. So those the patients with high chronic diseases also at risk more than those with minimal or let's say less than 3. So as an overall insight, we can say that interplay with or between the biological, social and health factors interact to shape the sarcopenia risk in older adults. As for discussion and further direction, we can tell that this is the first estimate of sarcopenia risk in Kuwait. The promotion may be high compared to the global. And as I said, here the results reflect the risk, not the prevalence, as we didn't use the muscle mass measurement. There is a few Arabic studies and conducted in this field, and the variability was due to the different methods, some of them using imaging, some of them using screening like us. And the gender, as we said, the female has higher risk in Kuwait, and this is consistent with Saudi study. And maybe the reason for that or the justification is the cultural factors, as we said before. The rising obesity in the Gulf countries also amplify the sarcopenia risk. So as we talk about sustainability, we have to come up with a model to help with the sarcopenia. So this is a sustainable prevention strategies that I recommend we can use it, or the physiotherapists also can use it, which is a start to implement or integrate the screen, which is the SARC-F annually, using the Arabic version in the primary clinic to identify those at risk of sarcopenia. And then, as you see in number 2, we will integrate or enroll those at risk of sarcopenia in a group strengthening or resisting training. After that, we can do also counseling with help of nutrition regarding the protein and vitamin D intake. And for those who suffering from fear of fall, okay, we can also provide for them balance training for fall risk, and at the end we can monitor or check or track the progress using the functional test, which is the mobility and strength. The implication of our study was that a SARC-F is easy questionnaire. It can be used. This is an initial estimate that can be baseline for further studies, and large sample study can be used in the future. As I said, the further direction, we already almost at the last stage of the translation validation of the SARC-F to Arabic version, and we are initiating large national study. As conclusion and take-home messages, 1 in 3 older adults at risk, females affected more. The results reflect, as I said, risk, not prevalence, and the functional decline is common in our country, and physiotherapy-led prevention is feasible. I'd like to acknowledge my research team, and before that I'd like to acknowledge and thank Kuwait University for the generous funding and sponsorship for our research, and also my colleague Dr. Ali and Dr. Maad Al-Haddad, who are both of them were co-author with me in the study, as well as the physiotherapists who help in data collection. Thank you very much.
Thank you very much, Dr. Alenzi, for presenting your research. We have time for questions. Are there any questions? Please.
Thank you, Dr. Latifa, for the nice presentation. This is Engineer Mustafa from the Electronics Department at KCST. Yes. I have 2 questions that are related to each other regarding the characteristics of the sample you took. Yeah. You mentioned in the slides the Marshall status, but you didn't relate it to the association keys. Does the Marshall status affect the results?
Actually, it's not, but we aim to ask for it in our demographic, and there is another minor question connected to this one, which is if they are living with the core or the, let's say, the big family, or they living alone, just to see if they're having a caregiver with them or not. This is but actually it's not significant, to be honest.
Yeah, and regarding the educational level, you mentioned that the people with higher educational level had less chance of getting this sarcopenia, right?
Yeah, I said those who have lower educational level
have a higher chance.
Yeah, having high risk of sarcopenia, and this is was interesting for us.
What could be the reason?
Well, for me, and even in our discussion for this paper, as I said, it is already endorsed for publication. We thought that maybe because they follow the national norms, maybe still they not familiar or not, you know, the importance of exercising, of daily exercising, the importance of going out, socialize, go out and doing, to have the sun exposure outside. I don't know, maybe these are the reason, but still we are investigating this, to be honest.
Thank you so much. I appreciate
You're welcome,
it.
my dear. Welcome.
Okay, thank you very much. Any other questions?
Hello, doctor.
Yeah.
Thanks for your nice presentation. I have two questions.
Yeah.
The first one is SARC-F is purely questionnaire-based responses, right?
Based on what, sorry?
Questionnaire, right?
Questionnaire, yeah, self-reported
So how do
questionnaire.
we validate
Yeah.
the answers given by the subjects or is a correct answers or true answers?
Actually, this is, all of us know that if we're gonna use a self-reported questionnaire, there is a bias in it, yeah? Because there is a there is a factor of recalling things, for example, or whatever. Sometimes even the participants will improve themselves. For example, how many times do you fall? One of the questions. They may say, no, I didn't fall, and they fall 3 times within the year, for example. All of us know this. This is why we combined it with objective measures. So we're not relying in one outcome measures, which is the self-reported, that can weaken the study, and at the same time we are improving the robustity of the findings with combining the self-report measures with objective measures.
Okay, thank you, doctor. And
You're
one
welcome.
last one.
Yeah, sure.
Regarding the study is concerned,
Yeah.
do you believe that the score might be different if you are doing a study with different nationality, with the different gender, different comorbidities, you know?
Actually,
Age.
our sample was fruitful, to be honest. However, as I said, the gender, the male were more than the female, and this was due to the also, within the time of our study, this is what we got. And as you know, this is community-based study, and we are looking for the feasible, available, eligible participants. And maybe the male are more encouraged to participate than the female. But actually, we include all the participants in the study. And as you say, your question, for sure, it depends on the culture of that context. It depends on the environment of those people. In Kuwait, we took Kuwaiti and non-Kuwaiti. We didn't just base in Kuwait population. So it is in Kuwait, but including Kuwaiti and non-Kuwaiti living in Kuwait. Yeah, you're welcome.
Thank you very much for your good presentation.
Thank you.
So, yes, please. One more question, and then we'll move to the next session.
Yes, Assalamu alaikum.
Alaikum salam. Hello, Dictora.
After the Professor exoskeleton robots, do you think that your patient, if they undergo to this exoskeleton robots, will enforce their muscles?
Actually, this is what one of the points that I aim to mention it during the discussion part of my study, but when they told me about the time, I forget. Actually, the innovative technology and assistive technology, together with the robotic rehabilitation, can be, it can provide targeted strengthening training for those with sarcopenia, okay, and also can improve the mobility support, helping the physiotherapy or the physiotherapist deliver personalized intervention to compound or to address the sarcopenia. These solutions not only enhance independence, to be honest, but it's also aligned with the global efforts of sustainability, as we said in the Kuwait Vision 2035, and also the Sustainable Developmental Goals. Thank you very much. Yeah, thank you.
Okay, let's move to the next part of this session. It's a panel discussion, and I would like to invite the moderator of the panel, Dr. Mohammed Naji. Along with the panelists, Dr. Alenzi, Professor Fayyad, and Dr. Yahut. Please come to the stage. So I assume I have already introduced two of our panelists. Let me introduce the moderator of our panel. Dr. Mohammed Naji is an associate professor in the Department of Computer Science and Engineering and the director of Center of AI and Robotics in Kuwait College of Science and Technology. He earned his MS and PhD degree from King Saud University in 2012 and 2016, respectively. Prior to his current role, Mohammed served as an assistant and then associate professor at the College of Applied Computer Science, King Saud University, where he also supervised the Innovation and Entrepreneurship Unit. And Dr. Mashaila Yahut, who is the founder and owner of Myco First Co., a pioneering company in Kuwait specializing in the management of advanced medical and rehabilitation center. Since 2019, she has led the introduction of world-leading Japanese rehabilitation robots officially registered with the FDA, EU, Japan, and Kuwait. Through Myco First Co., she has played a central role in bringing cutting-edge robotic therapy solutions to the rehabilitation sector and enhancing patient care in Kuwait. Please.
Well, good afternoon and welcome. It's my pleasure to moderate the Innovation in Robotics and Rehabilitation for Disabilities panel. In this panel, we will explore how robotics, AI, and rehabilitation technologies are enhancing the life of individuals with disability. I am happy to introduce our distinguished panelists. I think Professor Abul Fadl already introduced us, so I will go Dr. Latifa, Professor Samer, Dr. Mashail. Welcome in this panel. Well, actually, I will start with Dr. Latifa. Yeah, based on your experiences in physiotherapy education, what are the most promising opportunities for integrating robotics in training program in Kuwait? I think there is a problem.
I think it's working, yeah, thank you. Thank you very much. First of all, thank you very much for inviting me to this panel with my colleague here. Thank you so much. So in regard to the opportunity for Kuwait to integrate this innovation in our for example, physiotherapy education. Actually, as I said in my talk, that Kuwait vision is heavily emphasized the healthcare or improving the healthcare and even through the education. So the Kuwait has a strong healthcare infrastructures and growing interest in the innovation aligned with the Kuwait Vision 2035. So the key opportunity lies with the simulated-based learning, the robotic assistive devices for musculoskeletal and neuromuscular disabilities, for example. Actually, the robotics can enhance the clinical reasoning. Okay, can help. It can replace, to be honest, it can replace the human or the physiotherapist. And this is, this is the fear through all the world. For example, now I'm having a course with developmental training course in AI for educator with partnership with Cambridge University, and still all the experts there, they are having the same fear, which is they are afraid that it's replaced the human, or it's they are afraid that it replaced the educator. And for sure, and of course, and more confident, I can tell no, it can't, because whenever if it's convincing the AI, it's convincing. It's still need our mind, the human mind, to review it. And as I said, one of the opportunities is the clinical reasoning. Also, I encourage pilot program. We can't go for it without piloting a program, to be honest, to know the strength and the weakness of it in our rehabilitation, so we can bridge the theory with the practical before we go for it. Thank you.
Who knows that? Maybe in the future.
Yeah.
Yeah. Professor Samer, from your academic background, how have robotics research helped making rehabilitation more effective?
Actually, rehabilitation take benefits from robotics at many levels. One of the levels that we can ask robot to do repeated and precise job. I mean, this is maybe more hard when we ask users or expert to do it. This is the main point, that we can ask robot to do the same job for n time and then to find the same results. This is the first point. The other point that it's more useful with robots to, and even while including AI, to give a personalized service. So I mean, if you want to come and to do kind of physiotherapies on me, and if you apply this on me in the morning, it's not the same things if you applying this in the user in the afternoon or after some physical activities. So robots with AI can be adapted to a personal application, which is very useful. Also, one of the point that with robot it's very easy to measure, to take information, and those data will be very useful for experts to analyze and to understand what's happening. So actually, I mean, as I try to do in my presentation, naturally the human robots coming to exoskeleton, and then we go to rehabilitation things.
Yeah, okay. Thank you, Professor. Dr. Mashal, as someone who is working directly with robotics and rehabilitation in Kuwait,
yes.
Yeah, how have robotics improved rehabilitation effectiveness and patient's outcome?
Well, we see tremendous outcomes from the patients. Like we see today, the MS patient, which is in the medical theory, they say it's impossible for her to come back.
Yeah.
And she said it herself that she was rated in England that she will be handicapped for the rest of her life. We tried with her for one day and another for 3 months, and we see tremendous outcomes. And the first time we went to her, she said, I feel something in my foot. So we said, okay, let's take the challenge. And after the 2 months or 3 months, we stopped. We said, we want to see if you go back. But it was okay. She did not deteriorate or anything in the nerves. Then what you saw today is the outcome of 1.5 months continuously, daily measures. Everybody was happy,
yeah,
and I think
everybody was happy today. Yeah,
and she's not the only patient. We treated Parkinson's disease, we treated DMD, we treated Charcot-Marie-Tooth, we treated, of course, the strokes is for us is something very natural. But for the really 8 neuromuscular diseases, which is MS is considered some of them, it is really a very encouraging baseline to start in Kuwait and for other people. And people are really interested, and speak of the mouth, they just come. Yeah.
If you don't mind, just want to ask. So who were treating them, Dr. Mashal?
The physiotherapists, who are very yeah, because what is the people is considering doctor what she's saying, people are scared from the robot. We see that whenever it happened, the robots cannot replace the human factor, because the human we are doing with the humans. Maybe the physiotherapists will be less, but we cannot replace the human in this criteria. We need somebody to operate and to talk to people.
Actually, exactly, because this is why I ask who treating them. So it's not the robotic itself.
No.
It is the physiotherapist. There is an interaction between the robotic and the physiotherapist, and without the physiotherapist, the robotic will not work, because we need to detect the signals, and no one will understand it other than the physiotherapists with
Yeah, yeah,
the
sure.
specialty. Yeah.
But at the end, they use the robotics in order to...
Yeah, we integrated.
this-
Integrated in the rehabilitation.
Yeah, this is
Yeah,
the
I would like to ensure, because as a robotician guy, I would like to ensure the two ladies that we are not, our objective is not to replace the human, actually to give a tool to facilitate
Yes, you're right.
the job.
Well, Dr. Latifa, what change should university make in their curriculum to prepare graduates to the future, where the robotics and AI drive the rehabilitation?
Actually, we are revising our curriculum annually, okay, and we are almost going for a new curriculum now. I can't promise that we will have it near. Still, there is because it's under investigation, okay. But from my point of view, and I will talk this from myself, okay, as I am certified in Cyberdyne HAL, okay. I have the full training for the lower limb HAL, and I have an experience during preparing for one research, as you remember last year when I presented here, that integrating the robotic for the neuromuscular and musculoskeletal disabilities. Actually, I feel that introducing interdisciplinary course is important, because as I said, physiotherapists alone will not understand because it's more about engineering, okay? So we need physiotherapy in that course, we need biomedical in that course, and also we need an AI fundamentals courses, okay? So we have also, I suggest to develop a joint project, okay, and program. So the student, so the student will design for us this and test the robotic and rehabilitation. This is important things before we go for it in our curriculum, okay, and also include data analysis and human-machine interaction modules, because how they will understand these
This is
things.
my second question to you.
Yeah.
Actually,
To
Professor
add-
Samer, in
sorry,
terms
can
of...
I add one point actually?
Yeah.
Exactly, this is what we did in basically. They push medical doctor to follow at least one lecture from technology, and they ask engineers from technology and robotics to go to medical faculty to follow at least one lecture to understand what's happening. So we are doing kind of multidisciplinary interaction between fields.
It's important, yeah.
In terms of robotics, Professor Samer, in terms of interaction between the human and the robot, what are the biggest obstacle or difficulties that you are facing during the development of the robotics for rehabilitation?
There is a lot. Don't worry, we will not replace human.
Yeah.
Actually,
I mean the biggest.
Yeah,
challenge
one of the
that you
biggest
face.
it's about security.
Security?
Yeah, how to have a safe interaction between the robot and the
Safety,
the human.
Yeah.
So how the robot can be able to produce enough forces to move the body of the human, and at the same time to be safe. This is one of the problem. We try to solve it by proposing a solution mixing electric and hydraulic. Because I mean, if in robotics, if you ask me to produce more force, I will put more motor, and then more motor. This means more power motor.
Power,
this
yeah,
means,
more power.
more risk to have something. This is one of the obstacles. Then we have obstacles about detecting the intention.
Sorry, detection?
Detecting the
attention.
intention of the user.
Yeah.
So I mean, we try to use with some exoskeleton or orthesis and with the IIG. So we measure the electric signal, and we try to understand what's happening when the user want to walk, but it's not clear all the time. I mean, the robot can decide that the user is walking, but in the reality he is not walking. He is falling down or something happened.
Yeah. Have you applied AI in this terms?
Yeah, of course. I mean, AI, machine learning, it's this place. So we have problem coming from mechanical problem. We should develop more mechanical part with the green technology that can use easily. We have problem with electric. We have problem also with AI. Should be more adapted and more personalized for the person.
Yeah. Yes.
But we still have the main obstacles at the level of hardware. So because we see during the last years, we see a very advanced in AI, but the hardware, it's still the obstacles. Yeah. This is why we need a lot of time before trying to replace a human. Yeah.
Yes, okay. Dr. Masha'il, based on your experiences in Kuwait, what are some of the most impactful robotics rehabilitation success story that you have seen?
Well, today you have practiced one of them.
This, yeah.
Yes, and we practice also a lot of the new muscular diseases. We see changes. We see a lot of development, which before we cannot see. Like DMD, we see people starting to stand up, moving with their hands, and this is dystrophy. Dystrophy for the muscular dystrophy, it's impossible. So we do see a glance of light for children, also so for the cerebral palsy. They are getting back. A lot of research has been done in Turkey for the cerebral palsy, in Italy, in Germany, in Japan, Malaysia. So we talk all together, and we do see progress in this.
Okay, thank you.
You're welcome.
Dr. Latifa, from educational perspective, how can university ensure the ethical principle in their program as the robots and AI are using for rehabilitation?
Actually, as a physiotherapist and healthcare provider, okay, we know that there is a specific ethics for the healthcare provider or when we do anything regarding the health. But the ethics now in this situation, it should goes beyond the healthcare ethical to the to include the robotic specific issues. For example, the consent for the patients, the patient autonomy. So to have their consent for using the robotic for them, for example. This is one important thing. The other thing is the data privacy and the cyber security, okay, of the data. For the AI-driven rehabilitation system, we have to ensure it as well. Also the bias and the accessibility, so to ensure the equity for all the patients, let's say, or those who are gonna have this rehabilitation through the robotics, to make sure it's not only for the high resources. As we know, it's expensive. The robotics is not a cheap or method or material for the rehabilitation. It's expensive, and as from the ethical point, we have to make sure or to avoid the to prevent the bias of this one. For example, we just use it for those with high resources or for those with high resources setting, for example. This is very important and critical. Universities can embed ethics through the case-based learning. When we teach our students, usually we use this like assignments. Usually we bring a real case study from the hospitals for the students, and we train them on these cases for their clinical thinking, for their clinical reasoning, how they will assess it, how they treatment, and we make a great discussion together in the class during the one-to-one or in-person teaching. Also simulated scenario, and I'm also excited to share with you that at the beginning of September we did a big research about the clinical simulated research in our physiotherapy lab. So we simulate the BT gym or in the hospital to Kuwait University. We already started that, okay? And we do it, yes, for many skills, and we are happy to do it as well for the robotics in the future. And it's give a really embarrassing or impressing, results, because after 2 months or 1 month of their joining their rehabilitation or placement in the hospitals, we recognize, because it's randomized control trial, we recognize that the people or the students who were in the experimental group and they having the clinical simulated with the clinical instructor one-to-one do a great job in their midterm assignments or their grades, and even from the clinical competency scales with their clinical instructor in the hospitals.
Great.
Yeah.
In terms of designing, during the designing and development process of the robotics, is there any ethical principle that we have to care about?
Of course, I mean a lot of, and then usually robotician guy and mechatronics guy, they don't know, and they don't have to think a lot, because we train them to solve equation, to find solution, and then this is why, like in our university, if the PhD student he want to work directly with in a robot that will be on touch with the user, the doctoral school will ask him first to go to follow some ethical program. Sometimes it's online, but he should finalize this and then go back to his research. This is in case that his robots will be in touch with a human. I mean, because he need to answer some contradictory question. From one side, informatic guys, they will try to collect a lot of data because it's useful for them. If you ask me to programming a robot to go between the shares, I will try to collect the maximum data because it's useful for me. But maybe it's not ethics. I mean, from an ethics side, we should collect the enough and only enough data to do the mission, not more and not less. This is very important. I mean, it's one of the big problem. We are trying to make it clear for the user why we are collecting this data and to what end. And there is a very hard protocol, but I mean we still need to work more from the engineering side to train those engineers to respect those rules. Because he has a lot of rules to respect from the mechanical side, from robotics, and then we said, okay, you have one more rules from ethics, and it's not easy to accept.
So we have to consider those ethics.
Of course, naturally.
From clinical perspective, Dr. Mashail, what kind of ethics that we have to address?
Well, we have to be careful while dealing with the patients. Some patients, they are scared from any AI robotics, so they will not apply it. So you have to talk to them how the application will become. Also, the other procedures for like ethically, we have to take care of the patient, not to give any information about them. But today, of course, we saw a very brave woman. She decided to show people that they can follow her.
As a case,
yes, but we see that a lot of people, they said, we don't want our faces to be shown. Although in our protocol, we have to take videos for before and after, because most of the patients, they do not believe that they become good.
Yeah, but what about the privacy in terms of taking a video for the patient?
Yes, we are not allowed.
We
are not allowed, and if anyone he wants to
record the video.
Yeah, no problem. If he say, we have to sign him, and if he agree. If he doesn't agree, by not showing the face, we can, and the lower part, to show just the body, and the seconds matter to us for the progress of the
like an evidence, you use it as evidence before and after.
Yes, evidence. Even in the researches that's been done around the world, it's been done, the same protocol is being done. Have to be like that.
May you please tell us more about the protocol that you use, if you don't mind?
Yes. First of all, we do the checkup for the patient, whether he is eligible to do the or not. We do have some restrictions.
Of what? I'm sorry to interrupt you, but
what? Like a pregnant woman, she cannot. And like some kind of severe osteoporosis, we cannot. And some kind of for children or somebody that we cannot tackle them, because they will not understand the mechanism of the robot. Because this kind of robot, the brain sends signals to so they cannot interact good with the robot. That's all. So after also the videos, and then that's it.
Okay, good. Yeah. Sure. I know that we are out of the time, so I'll just ask our panelists if you have anything you need to add. Please, Dr. Latifa.
Yes, one of the important things I'd like to add with the robotic rehabilitation is the human-robotic interaction. the empathy. Okay, so even if the empathy to the patient, so even if you are using robotics, still the physiotherapists, they have be empathetic with the patient, and this is one of the important things, to be honest.
Yeah, Professor Samer, yeah, please.
So actually, one of the still open question we need to work from the robotic side, it's the social acceptance. As Doctor mentioned, I mean, we develop a robot and we don't know why I accept it and why you don't accept this same robot. And we don't know, it's the social acceptance, it's still a main field to work on. And then we need to develop more flexible robots, more compact robots, to not be, to increase this social acceptance. Yeah, exactly.
To reduce the gap. So
to
this
reduce
is your,
the gap and to increase the acceptance.
this is your responsibility.
In the future,
I need help.
future approach.
I mean, as
And
a
the project.
scientist and researcher.
Yeah, of course.
Yeah,
I mean, there is
yeah.
a lot of job to do on this direction.
Dr. Michel, please.
Yes,
Go ahead.
I think people now, after how many years? 4 years, we're doing, in clinics, and people are little by little, adapting the robot. They keep asking, and when we explain, and sometimes we have to do on ourselves, they will accept it, and they will do the challenge. And a lot of even children we practice, they love it, because the robots, they have special songs or something that will make the child a little bit active. So
they are playing with the robot.
Yes. So we do.
Yes.
We do have a 3 years old baby.
Oh, baby.
Yes.
Oh.
And she managed to recognize after 8 sessions only, which is a breakthrough.
Amazing. Yes.
Yeah. Sure.
So thank you for being with us today for this.
Thank you very much.
Amazing panel. Yeah.
Appreciate
And
it.
also I would like to thank you all for joining us.
Thank you very
in this
much.
panel. Thank you.
Thank you very much for the very good discussion panel. So please
Is
stay
there
on
any
the
question?
seat.
Yeah.
And before leaving, I would like to invite Professor Jimmy to give a token of appreciation to our panelists. Thank you.
No question.
We have networking, right? We have this. Start. Good afternoon, everyone, and we would like to continue with the technical session 1, integrated solutions for accessibility from IoT to robotics. I would like to call Afef Kashim to present his paper on Parkinson disease severity assessment from gait patterns, CNN transformer hybrid approach. So, is it Arich side? Kashim is available online? Okay. coming. You have.
Good afternoon, everyone. It's a great pleasure to be here to present our research on Parkinson's disease, also known as PD, severity assessment for gait patterns, based on the CNN transformer approach. So, I'll begin with the hard truth. Do you know that globally more than 10 million people live with PD? Let's dive deep on how to recognize PD and why timing is matter. Okay. In fact, imagine that your body slowly refusing the move you want to move. Your hands shaking, your work unsteady, and even your voice becomes softer. This is the reality of millions of people over the world, and this is the Parkinson's disease. In fact, it's more than just shakes. It's a progressive brain disorder that steers movement, stability, and independence. It happens when dopamine-producing neurons in the brain are lost, and the exact cause remains unknown, and the damage can't be undone. The hard truth, The hard truth, it's chronic, it's progressive, it has no cure, and the number of cases keeps rising yet. So this isn't just a medical challenge, it's a race against time. Well, here's the key. Early detection can change lives. The sooner we act, the more we can fight back. But detecting its severity early is still a challenge. So the objective is to propose an automatic and objective tools to detect PD and assess its severity early. In addressing the matter, I will begin with medical context, then I will present research objective. Afterward, I will review the state of the art and describe the proposed solution. Then I will give the obtained results and finally conclude with some future prospects. Identifying that a patient has PD is good, but knowing what stage they are at is crucial for treatment precision. Is it in stage 2 where life is manageable, or stage 4 where daily task becomes a struggle? The treatment and the support are completely different. In fact, your work tells the story. Being able to predict PD progression from something as simple as how someone walks, shuffling steps, or sudden freezing. Those small changes tell a story. And the objective is to propose a smart model to detect PD severity early just by analyzing walking patterns. This brings us to a critical biomarker, which is the gait, how a person walks. Subtle changes like reduced arm swing, shorter steps, or uneven rhythm can be early signals of PD progression. And why it matters? Because early detection starts with understanding small changes in movement. Let's move to the state of the art. Most EI models, such as ConvNet and Transformer, miss key details and can't pinpoint severity stage accurately. So we can do better. This is the key limitation. In fact, we face 4 major limitations. 1D ConvNets struggle with sensor data relationship. Second, transformer miss fine-grained local patterns. Third, unbalanced data, which reduces model accuracy. And fourth, few models can accurately track disease progression through its various stages. So without solving this, early and accurate detection remains a challenge. So what we propose a 3 solution, smart hybrid models for precise PD detection and staging. First, Inception 1D transformer, which combines multi-scale feature extraction with attention for richer analysis of the data. Second, LSTM transformer, which has the advantage to track complex gate patterns across time and space. And third, Conv BLSTM transformer, which learns context bidirectionally from sharper insights. These advanced models allows us to have better accuracy, clear severity staging, and most importantly, no missed details. So the data behind our research is FusionNet Gate dataset. It's measured working under real-world conditions, which compared 93 Parkinson patients with 73 healthy control, all with a mean age of 66. And this is our input data. It's about 1D vertical ground reaction force, signals from gate, essentially measurement the force from walking using AT captor sensor. To prepare our data, we broken down signals into individual gate cycles. We scaled data for better model learning, and we balanced data to represent the different stages equally for the model. Well, this is the overview of the reference model. As you can see, it uses a mix of convolution and transformer blocks, both temporal and spatial, to effectively analyze and classify the input data into 4 classes. Classes 0, which is healthy, classes 2, classes 2.5, and classes 5. So to enhance the CNN part, we proposed 3 solutions. First, we used Inception 1D for feature extraction, which effectively captures multi-scale gate patterns in one model, which is ideal for detecting Parkinson's disease degradation across varying temporal scales. Sorry for the error. The second model we proposed is ConvLSTM, which has the advantage to capture both spatial and temporal gate features. And the last one, which is ConvBLSTM, it combines the pattern finding strength of convolution layers with the context understanding power of bidirectional LSTM. To train our model, we used NADEM optimizer with learning rate of 0.301, and we used categorical cross entropy loss function. The training uses batch size of 150, and we used 4 blocks of transformer with 2 heads. This is the result we obtained from the reference model. As you can see, it it performs well. We achieved 0.89 as accuracy, but the main issue is distinguishing between severity levels, especially the most severe cases. For the first model that we proposed to enhance the feature extraction, which is the Inception 1D transformer, we obtained 88 as accuracy. The key improvement that is better at identifying severity 2.5 cases compared to references model. The second model, Conval-STM, it achieves similar accuracy as reference model, but much worse at detecting severity 3 cases. The last one and the best, we achieved 94% as accuracy, and it's the best performing model so far, effectively handling all cases. When compared it with some related works of the state of the art, we find that it's significantly outperforms all other methods across all metrics, demonstrating its superior performance for this task. Donc, as a conclusion, assessment Parkinson progression from gait is crucial, but challenging due to subtle complex patterns. Our solution is a CNN transformer hybrid models optimized with Conv-BLSTM, which captures details and long-term gait feature, achieving almost 96 accuracy and severity classification. Looking ahead, we aim to deploy it clinically and add explainability and enable personalized treatment for better patient care. To end, I have to say that such technology do not replace the doctor, but it's empower it with better tools, so better treatment and for better quality of life. Thank you very much.
Thank you. Thank you very much for your wonderful presentation. The floor is open for question. Anyone question, please?
I'm Aida Rouzi from Latisla, University of Tunis. Thank you, Professor Afif, for the interesting presentation. And I want to know if the severity stage of Parkinson's disease can be assessed by characteristics other than walking, and how? Thanks again.
Thank you very much for your question. Yes, absolutely. The Parkinson's disease is complex. It's a complex disease and can affect many functions in the patient. In addition to walking, researchers studying other characteristics such as the voice, which become softer and monotone, the handwriting, which can become smaller and shaky, facial expression, which can be less marked. So we can think about multimodal detection of this disease using different source of information. But when combining these different sources, we had to build a complete database, which is not obvious. And to think about how to merge these different features intelligently.
Thank you so much. Yeah. So. Okay, let us move on to the second presentation by online. So the second presentation by Imran Khan on the title of Smart Design Applications transforming well-being through innovative solutions. Okay.
Good morning. This is Dr. Imran. I'm going to present my article with the title Smart Design Application Transforming Well-Being Through the Innovative Solution. In Portugal, last few years, the retirement age is increasing by every single year. And due to the retirement, that the people's, the first thing happen when you get retired, that is your social circle decrease or get shrink. Because before that, before the retirement, you are going to work and you have a more big circle with your colleague, with your customers, and your social circle is bigger. Now, once you get retired, the one thing impact in your life, that is you will have a smaller social circle, and that increase social isolation among the older adults and reduce their outdoor activity. What happens once you have a small social circle and less outdoor activity? The first thing happens, that is psychological. You impacted the decrease of psychological health condition, and second one, decreased physical health condition. You start having a mental issue, you start having a psychological issue, you start having a physical health issue. To contain this, we introduced an application that has two perspectives. The one is intention communication. In this, the old people can talk, interact, participate with the other people by using the social media platforms, and also they can do outdoor activity to go outside with their peers and family members to enhance their outdoor activities. The second one is the passive communication. In this passive communication, that people can, you can say, especially the medical personnel, can monitor the older adults from the long distance. They can monitor their physical data, including their body temperature, fall detection, heartbeat rate, the pulse rate, and the blood sugar, and so on. And secondly, the family member also can monitor their older adults, their physical data, and about their geolocation. The objective is to sketch, design, and validate IoT-based social hybrid model that should have a capability to promote well-being among the older adults. And secondly, we have to understand this kind of application can have a capability to promote physical, psychological, and social well-being among the older adults. For methodology, first we design, you can say, or define characteristic and feature of a conceptual model, and then we validate it by doing the online survey. Our study object and the subject is IoT technology and physical, psychological, and social well-being of older adults. The target population was selected up to 60 years because we think that we should take the population that physically, mentally fit to answer and validate our conceptual model, so that we didn't cross more than 60 years and we don't want to work with the fragile people. For recruitment process, the first we find the senior university in Portugal by using the Rootis Universidade platforms, and where we got university information, especially the email, social media account, their website, and we found like 411 senior university in Portugal, in which the 398 university on mainland and the 13 university are island, Azores and Madeira. We contacted with them by sending the email on their official email account or their official social media account like a Facebook or Instagram to enhance or make our reach more effective. In the survey, before starting the survey, so we share with them our animated video, and this animated video like describe what this design can do. So let's watch first of all this animation video. Secondly, we showed them our Figma prototype mobile application, and in this, the people can experience how this mobile application can work. First of all, registration. Then we have different options that people can select it and experience how the application works. So participants interacted with the prototype application design in Figma, and we think that they should have experienced how the application is work, allowing them to explore the various scenarios and provide the feedback more effectively. The results indicate that we have 411 universities, in which 398 universities from mainland of Portugal, and 18 from 18 different districts, and we have 13 senior university from the Portuguese island, like Azores and Madeira, from the 2 different districts, and total is 411 university from the 20 districts. In this study, 36% male participated, that is equal to 64, and 115 female participated, that is equal to 64%. And we have like how many people are working, unemployed, or retired. So we have a bigger number, that is retired people, that is 138 people participated, that is the total 77% of the sample. We divided our application survey in 4 different parts. The first part is a social interaction with the family and friends. And these results indicate that the green part and darker green part indicate that 80 to 85% are agree that our application provides social interaction with the family and friends and with the other people to enhance their social well-being. And the same with the medical follow-up, that the most of the people are agree with the 80 to 85% are agree that our application provides physical and data monitoring mechanism that is helpful to improve their physical well-being. And people have opinion about application and that what are the advantage of our application. If you look at the result that indicate that this application has advantages and that can improve the well-being of elderly, and that can improve their social well-being and psychological well-being and their physical well-being. So some people try to raise concern in this application, in this survey, that security and safety, that we try to convince in the system and in the video and in the Figma prototype application that we have one layer, and that layer that give us upper hand to the user to protect their privacy, because once the old people are going to share their very private thing with the stranger or with other people, the notification go to the family members and they will take precaution measures. The results show us that the design of this model have ability to promote physical and social activity among the older elders and reduce their social and physical isolation. So once people don't have too much social and physical isolation, definitely it will improve their physical and social well-being. This study, we have 179 participants that sample can be biased, limited generalizing or finding across a diverse demographic. So this is very small population that represent the Portuguese whole population. So we think that we have to do a little more research and enhance the numbers, and that represent the whole population of the Portugal. The data privacy insurance, while participant trust in system security concerned about the unauthorized access and data monitoring must be addressed to build the confidence. So we already addressed in the application that their data is not going to be compromised once the old people are going to share their data with anybody. Before sharing, the notification go to their family members, and they can take any precaution measure to protect their data. Establishing ethical practices, so reverse privacy protocols and security informed consents are essential for ethical research and application development. The future implication ensuring the focus on ethical development and compliance with the regulations like GDPR and HPAA will be support the successful adoption of innovative health application. If you have any questions, any doubt, any concern about this presentation or articles, please send me email on my email is imkhan@kane.edu. Thank you very much. Have a very lovely day. See you around. Bye-bye.
Thank you so much for the presenter. And now we move on to the next presentation from Dania Abdul Sami from Kuwait, and I'd like to request her to present her work on distributed assistive IoT with the electrospun piezoelectric nanofiber self-powered sensing on an open protocol edge architecture. Yeah, the floor is yours. Yeah, please.
Okay. Yeah. Okay, thank you. All right, good afternoon, everyone. My name is Dania, and this work is titled Distributed Assistive IoT with Electrospun Piezoelectric Nanofibers Self-Powered Sensing on Open Protocol Edge Architecture. This work has been realized within KCST at the Center of Nanotechnology and Photonics, as well as the Lab of IoTs, and networks, along with the co-authors that are also under the same affiliation. Okay, so distributed architecture for safety-critical assistive IoTs. It follows usual current systems that are under assistive IoTs. They follow a cloud-dependent, opaque, power-constrained systems that are quite hub-centric. Our goal here and the aim is to move the existing assistive IoTs to a more distributed mechanism. They need to follow the distributed system mechanisms that have attributes such as fault tolerance, reduced single point of failure, less centrality, and therefore the key contributions can be as follows. We have designed an open protocol, local first, multi-hub design for assistive scenarios, alongside the fabrication of PVDF TPU nanofiber patches that are integrated within the assistive scenarios. And then for the evaluation matrix, it includes latency measurements, availability across daytime, calculations towards mean time of failure, mean time to recovery, safe state transitions, and false alarms. So the core stance here is that assistive IoT technologies are moved towards the robust systems we see in infrastructures that follow safety and security constraints. Okay. So people with disabilities, they depend on the sensing, dependable sensing, and timely actions for autonomy and safety. So usually, for a person with a disability in a wheelchair, any fault that could happen at the wrong moment could result in severe consequences. So it's a safety event at that case. So assistive IoT is designed in a distributed manner that are resilient against faults. They have fault tolerance due to the network having a high bisectional bandwidth and thus high fault tolerance. So we have the PVDF nanofibers, a blend of PVDF nanofibers along with TPU as an additive for flexibility, connected to microcontroller nodes, and then comes the multi-hub architecture, the two hubs, for example here, and they execute a replicated policy for deterministic local behavior. So this, at the end of the day, ensures a deterministic local behavior from the distributed system. And then the action could take place, whether it is whether we are triggering a particular action or sending, in some scenarios, a wide area notification. Okay, so more on piezoelectric material and the phenomenon of piezoelectricity that is possessed by nanofibers. Piezoelectric materials can be found in different material classes such as ceramics, crystals, and polymers. These nanofibers, they possess the ability that under mechanical stress, they possess the piezoelectric property where mechanical energy is converted to electrical energy, and then used for a spectrum of purposes. And then also, apart from energy harvesting possessed by PVDF material, for example, as a nanofiber we're using here, nanofibers possessing piezoelectric ability have also the ability to become sensors within our distributed architecture. So they act as sensors that send signals to our microcontroller to execute the commands we are after, and also as micro energy harvesters. And it's also known that the beta phase content within the nanofiber mesh increases the piezoelectric response from the material, and therefore enhancing this beta phase content enhances the piezoelectric response and the overall performance. Okay. So, as to the experimental methodology, materials and methods, we are using a polyvindyline fluoride, as the main polymer to come up with the piezoelectric material, along with TPU, 15% TPU thermoplastic polyurethane, that was sourced from Germany. It was incorporated into the formulation. And then for the electrospinning setup, the experimental setup, it involves a high voltage power supply of 25 kilovolts with an injection pump set at the flow rate of 2 milliliters per hour, a syringe with a needle and a conducting collector electrode. And as to the results, as we can see in the SEM photograph here, we can see that the mesh is quite dense and beads are low. This means that the fibers are smoother on the smoother end. And also looking at the FTIR graph, we can conclude that the beta phase content is high as intended for the purpose of great piezoelectric ability. All right. After performing some experiments, it was concluded that around 4 to 5 volts were achieved after independent impulses on the piezoelectric material. And then with continuous stimuli, we can achieve above 8 volts. And as to the airflow sensing, experimented at 4 to 12 kilometers per hour, voltage reached to about 4 volts. Okay. We have put some scenarios in place related to how the nanofibers are integrated within a wheelchair. The first scenario demonstrates the patches integrated onto the armrest or the footrest, and this is related to disabilities that have to do with paraplegia and quadriplegia, which is the inability to move the upper body or the lower body, and therefore we can accommodate those cases by integrating the nanofiber patches at the appropriate locations within the wheelchair. And the second scenario is for patients that deal with total immobility. Nanofiber patches are placed on the headrest or the seating in order to detect any cases where the patient is trying to initiate a movement. It could indicate sometimes an emergency situation. And then these impulses are then connected to the microcontroller nodes to initiate the action within the fault-tolerant distributed system for the purpose of achieving local and deterministic behavior. And then the third scenario is having patches placed on the footrest. This is intended for the patient in cases where the patient requires to do some deliberate tabs in order to push forward some sort of navigation or routine trigger input. Okay, and the oscilloscope readings here set at the sensitivity of 500 millivolts per division show that we have achieved the mentioned voltages at continuous stimuli of above 8 volts. And then the overall system performance we have achieved from our distributed architecture that is localized. We have achieved local executions of above 92%. Availability throughout the day was found to be above 99%, and false alarms detected were below 0.1 events per hour. In terms of reliability, because we are after reliability, after all, within the fault-tolerant architecture, median actuation latency latency was between 214 to 368 milliseconds, with a 95th percentile delays that are above 780 milliseconds. And then an SNR, impulse SNR is above 12 dB. So more results and evaluation scenarios are there in our paper, and I am now open for questions if there are any.
Okay. You are the author.
Thank you, Marquis. Yeah. It's not no, this is not, this is like an opening comment in order to have future work. So in terms of scalability, I mean scalability, now we have like a wheelchair, it becomes self-sustained in terms of a small light, it serves the purpose. But how can we think about a scalable solution where we have more, because we can, one of the, like someone can argue that the amount of energy you can get is very, you know, very limited. And I was talking with Dr. Bassem that now there is a big research happening for wireless energy transfer to charge drones and enter satellite. It's really very interesting. So even, although some people may claim that this is very low energy production, it may be, so my comment is not a question. We may, it's worth thinking about how can we make this technology scalable at the level of generating more. Probably, do you have any? Yeah.
So it's true that piezoelectric material does not produce a huge amount of energy at the end of the day, and it's not the purpose here. The purpose here is that the piezoelectric material is used for a triggering purpose and not for continual energy harvesting that is reliable. Okay, so reliability, when we talk about reliability here, we're talking about system availability as to the automations that take place, as to the policies that are implemented by the hubs. So as we increase, as we scale up with our assistive technology applications, such as the wheelchair application, we are pretty much looking at scaling up our distributed architecture that involves those hubs and all. And essentially, the entire system isn't meant to be powered entirely from the renewable energy source, the PVDF source, because that is not quite sustainable. Although the IoT devices are resource-constrained devices, which normally do not require that amount, a huge amount of energy to operate. That is true. But when I look at scalability, we look at the main architecture that we have seen here, which is the fault-tolerant distributed system that allows for the management of those applications under it, and then implementation and execution of the policies, the replicated policies. Although hubs within this architecture are sometimes redundant, and this is important for our fault-tolerant idea here.
Thank you so much.
Thanks.
May I ask you one comment? We have related to
exactly. So it's like in IoT, it acts as a relay to activate another process. So it's mainly to trigger something. Yeah. Okay. Thank you. Appreciate it. Thank you so much.
Thank you so much. Our last presenter, I would like to invite Mr. Mustafa Al-Hariri to present his work on towards inclusive university campuses, optimal planning of wheelchair charging infrastructure. Yeah, the floor is yours. You have 12 minutes for your presentation, 3 minutes for your Q&A. Okay.
Well, good afternoon, or maybe good evening now. Thank you all for staying till the last. As they say, save the best for the last. I'm sure of this. First, today I will be proudly presenting our research paper titled Towards Inclusive University Campuses, Optimal Placing or Planning of Wheelchair Charging Infrastructure. This research is a result of collaboration between myself and my valued professor, Professor Muhammad Rabelsi. So today you will be hearing a very good presentation. So let's start with the agenda of today's presentation. I will have a brief introduction and motivation. Then I will introduce the problem statement, literature review, research gap, and then I will propose our methodology. We will show the simulation results, and then we will have some conclusions. So first, where are we now? As you know, the current world population is almost 8.2 billion people. Out of this 8.2 billion people, we have 1.3 billion people living with disabilities, forming almost 15% of the world population. This percentage is large, and we have to take it into account. Therefore, currently, accessibility is a priority. This is according to the World Health Organization, WHO, and the United Nations. So let's talk about the local context. Here in KCST, we have almost 2,000 students, by which almost 18 students only have disabilities, forming not more than 1%. You might say that this percentage is very small. Why are we talking about KCST? The low percentage indicates that we need to build a better infrastructure to attract more students for future, because a significant number highlights the vital role and the vital need to have a better infrastructure for the mobility impairment students. You might say, what do you mean by mobility impairment students? Mobility impairment people use wheelchair in order to move. Currently or recently, we have wheelchairs that are electronic, and electronic wheelchairs for sure require frequent charging. So this is the problem, the frequent charging of the wheelchairs. Therefore, the campuses currently rarely provide a very safe and convenient way to charge the wheelchairs. You might say, we have a lot of sockets here. What are you talking about? You have to know that the electronic wheelchair does not use the regular wall socket that you use daily. They use a specific charging station that is costly to install. Okay, you might say, we have a lot of money. Let's install as much as we can. This is not the right way to solve this problem. So, in the literature, they say they focused on how to power this charging station, how to make it more better from the power aspect, and how to make it more convenient or more reachable for the wheelchair users. The problem is that we have three questions that we need to answer. How many chargers do we need? Where to place them? And what is the redundancy? How to place them, where to place them? Should we place them anywhere? Should we install 5 chargers, 10 chargers, 20 chargers per the floor? How many do we need? So to have the layout, for the research objective, we want to develop a lightweight, reproducible, and scalable optimized algorithmic framework to decide how many chargers do we need for the wheelchairs, for the electronic wheelchairs, and where to place them. And we will measure the coverage area, the coverage percentage, the redundancy, how much do we need. So this will be implemented in this research. So the key traits are, we will have near optimal results, very fast runtime, easily implementable and transferable to any layout that you need. You might ask now, what is the layout that you're dependent on? For sure we are here in KCST. So this is the system layout of KCST. I believe most of you here are in KCST, so you know that KCST is composed out of 9 blocks. starting from A to J. We are currently in block C here, as you can see, and this is the ground floor layout. We did a small survey asking the people in KCST, mixed between normal people and people with disabilities. What are the most visited locations in KCST? Most of them answered that cafeteria, labs, libraries are the major hotspots. And we asked them about the outlet accessibility. Do you have a good accessibility to the outlet? 32% agreed that we have a very good outlet accessibility. But the others did not agree on this. Regarding the preferred locations for the charging stations, most of them recommended to install them in the entrances, corridors, the cafeteria, library. For the redundancy, and when we say redundancy, we mean that each wheelchair is covered by at least 2 chargers in order, or in case of any charger gets a failure, we can cover it by another charger. So this is the system layout for the ground floor, and these are the system layouts for the first and the second floor. As you can see here in block C, where we are now, the lecture hall is spanning across both floors, so we are merging both floors in one layout. Now, what is our proposal? First of all, we have to define something called demand points. What are the demand points? Demand points are the locations or places where most of the students are present most of the time. Maybe cafeteria, labs, offices, clinic, counselor's office. So these are the demand points. So we have to define the demand points, select them on the floor layout, and the charger could be at any of these demand points. Then, the coverage radius. What is the coverage radius? The coverage radius is the reasonable distance that a wheelchair user can travel before they reach a charging station. We assume to be the R to be 50 meters, and you can vary it. You can make it 60 meters if you need less chargers, or 40 meters to make a better or a very accurate results and have more chargers. So we assumed R to be 50 meters. Remember this number for next slides. The distance computation, as you saw here, this picture will be uploaded to the software. How can the software know the real distance from a layout? These are pixels. So here we use this equation in order to convert the pixels in the picture to real distances known by the software, which is MATLAB. Then the weighted coverage objective equation. Here we define a new definition called the hotspot points. Not the demand points, no, the hotspot points. Hotspot points are the critical locations that we have to take into account and take it more seriously than the regular demand points. The hotspot points could be the clinic, the counselor's office, or maybe the most critical classroom. So the hotspots receive a weight of 3 in the equation, and the demand points, the regular demand points, receive a weight of 1. Then, the redundancy metric, as I said previously, the redundancy is when you have a demand point that is covered by at least 2 chargers. And what is the optimization method that you followed? We followed the greedy algorithm method, which at each iteration, it chooses the location with largest marginal gain. What do you mean by largest marginal gain? Assume we installed 1 charger and the coverage was 50%. Then we incremented the number of chargers to 2 and the coverage is 80%. Subtract 80 minus 50, the difference is 30%. This is called the marginal gain between the coverage, the current coverage, and the coverage at the next iteration. So we want to check what is the difference between marginal gain at each iteration. Now, you might ask me, why did you choose greedy? Why didn't you choose genetic algorithm or random placement or exhaustive or any other technique? We did a very quick comparison on different optimization methods. As you can see here, we did exhaustive search, greedy algorithm, genetic, simulated annealing, random placement. Among all of them, the greedy algorithm gave us the best results or the best combination of trade-offs of all the metrics, like the coverage, runtime, redundancy. You might ask me, in the runtime and the greedy, it is 0.08 second. However, in the simulated annealing, it's 1.8. There's no difference, it's only 1 second. But on a larger scale, you will find and you will notice the difference. So the greedy is the best one for us currently. But how can we run this simulation? A quick flowchart to make it easier for you. We start the code. The code is loading the floor layout. We calibrate the scale by choosing 2 points on the layout with known distance. We enter the distance. Now the pixel of the picture is converted to distance by the MATLAB code. Then we ourselves choose the demand points and the hotspot points. Your selection might be different than mine. It's fine. You can choose whatever you want. It's up to you. Then we set k is equal to 0. What is k? The number of chargers. The first number of chargers is 0. Then we increment k, make it 1, and add a charger using the greedy algorithm, compute the coverage and the redundancy percentage. Then display the results with the selected or the optimized location of the charger. Then ask yourself, is the marginal gain less than 3%? If no, that means that incrementing k is good. So go back, increment k and make it larger. If yes, if the marginal gain is less than 3%, this is enough. You don't need to add more chargers. Therefore stop, recommend this k and end the program. Now let's do a quick check on how to do this MATLAB code. As you can see here, this is the layout for the ground floor. We do this for all the floors, ground, first floor, second floor. Before I proceed, I would like to ask you a question. What do you think is the optimal number of chargers in the ground floor? What do you think? Give me your best guess. How many chargers do we need for the ground floor? No, only the ground floor. 9. Any other guess? 1 for the ground floor. This is not suitable actually. So first let's check how we run the code and then we will see the final result. Here I chose 2 points, and if you know this is F004 lab, I chose this location because I teach there the most. I am biased. So I know this location with the known real distance, which is 10.5 meters. Then after this point, the MATLAB now knows the real distance on the layout. Then we select the demand points, as you can see here. One might ask me, you are selecting all the points in KCST as demand points? Because we have a lot of students and they are very annoying. So all of them are demand points. Now you might ask me, why are you selecting demand points outside of the layout? What do you think? This is the ground floor. Why am I selecting points outside the layout? Smoking points, parking slots, outdoor sports area. So for the ground floors, we have a lot of facilities even outside the campus itself. Now, let's go to the hotspot points or the critical demand points. As you can see here, I chose the clinic, the student's counselor. Each block I have a critical demand point or the hotspot. Therefore, now we assigned the demand points and the hotspots. Again, I'm telling you, you can choose different selections than mine and you'll get different results. It's all up to you. Then, here we have the first result. The code placed the charger at block C and the coverage is 56.6%. Redundancy is 0. Why the redundancy is 0? Because redundancy means that you have to be covered by at least 2 chargers, and when k is equal to 1, there are no chargers, no two chargers even. So therefore, we incremented k to be 2. Now the coverage is 75.5% with a redundancy of 26.4. Now I want you to do some quick mathematics. 75 minus 56 is 20%. Is it less than 3%? No, it's not less than 3. So increment k further. Therefore, when we incremented k to be 3 with 3 chargers optimally placed at block C, block B, and block F, we received a coverage of 92.5% and a redundancy of 43. We further incremented k to be 4. This is all done by the MATLAB code automatically. We're not doing anything. It's just displaying the results. Now with k equal to 4, the coverage is 98.1%, redundancy of 60.4. We further incremented k to be 5. Here are the optimal locations with a coverage of 100%. So you said 9. This is not right. So 5 chargers are more than enough for the ground floor layout. 9 would make much redundancy. Now, to do a quick comparison, the ground floor, the optimal number of chargers is 5. The first floor is 2. The second floor is 2. Why did we have a number of chargers less in the first and the second floor? What do you think? Because we don't have external outside area than the ground floor. So therefore, the ground floor needed the most number of chargers in order to get optimal results. So as simulation results, key findings, 3 chargers fully cover 92 to 93% for the ground floor. However, for the first and the second floor, 2 chargers were more than enough to have a coverage of 100%. Controlled redundancy improves the user experience. This framework is scalable, transparent, and low cost. You can transfer it to an airport, to a mall, to any other building or layout that you desire. Now, there is a quote that says, "Eat yourself before someone eats you." So here are the limitations of our work. As you can see, we use Euclidean metric for the distances. The demand models assume static behavior. No real-time behavior was considered. The results are only based on simulation. Feasibility constraints for the electrical installments were not taken into account. But for future expansion, we might take these limitations into account and improve our research work. Now, as conclusions, with our study, which is effective and scalable framework, we got a high coverage with a minimal infrastructure. 5 chargers were enough for the ground floor, for example. We have a robust performance in which we have a high percentage of redundancy. The practical and transferable research where we can implement this on any layout from your choice. The cost efficient. This code is not costly at all. And strong foundation for future expansion. We can expand this work to better and take into account the limitations. And with that, we come to an end. Thank you for attending. Thank you so much.
Thank you so much for your wonderful presentation. Any questions?
Yeah, questions. Yeah, sorry. Yeah.
Why don't you try to use, in the future, don't you try to use the swarm intelligence optimization algorithm? Have you tried to use it?
No, actually no, because we only compared with these methods, which are
Like,
limited to our
swarm intelligence.
metrics.
Yeah, okay.
Sure, we can take this into account for future.
I mean, just a quick thank you for the nice interactive presentation.
Thank you, Doctor.
And this is, especially this slide, this can be expanded to many applications.
Which one?
Many applications, either wirelessly to node placement,
or the framework,
drone
you mean?
placement, this technology, like the
Yeah,
solutions. And you can consider this for even more interesting scenarios.
Sure.
Thank you so much.
Thank you, Doctor.
One more. Yeah, okay. If we stay at this slide, so you use greedy.
Yeah.
So how can you guarantee that the greedy algorithm gave you the optimal solution or near optimal and not a local optimal?
I mean, we apply this only on KCST. Maybe if we choose another layout, we might need another.
No, even from this layout, can you guarantee?
Because
this is the optimal one.
Because according to the runtime, it was the lowest, and regarding the coverage, they are almost the same. Only 0.3 differences between the greedy and the genetic. And for us, we didn't focus or insisted on a certain thing. The optimization framework is not the optimization algorithm is not the issue. We only
we're not saying it's the issue.
Yeah. Because it for this, yeah.
Saying that because of the runtime or whatever, how can you guarantee that this
Yeah. We started with the greedy, and whenever we were done, we tried to compare it, and we found that there was no significant difference, better solution. Yeah. Yeah.
You're stuck at the local minimum,
Mm.
and it's not the minimum.
Yeah, exactly. Mm.
I believe now for you have limited scenarios.
Yeah.
So for other scenarios, you need to explore this in order to have a clear, convincing and
Exactly.
answer that this is
The optimized.
or near optimum
Mm.
and not a local optimum.
As long as we have the code script for all of them, so we can shift between any of them based on the layout.
You need to compare to the exhaustive search at least.
Yeah, there is the exhaustive search first. Yeah. Sure, yeah. Exactly. But as we say, the coverage is not different between all of them. There is no significant difference. That's why. Sure.
Okay, last question, Mustafa.
Thank you.
What type of distance metric have you used? Euclidean distance or Manhattan, or what is the type of distance metric you use?
Euclidean.
But I think this is not right here because we don't have a continuous area or a square area.
Yeah, this is the problem is that we don't have the real corridors and the real movement was not taken into account, because this one needs a very more complex
you need
code.
to find another metric for the distance.
Exactly, this is why. Yeah. Thank you so much.
Yeah, thank you very much. Yeah, I would like to request Professor Mohammed Trabilshi to give a certificate to Dania. Dania, please come on the stage. Please, can I ask Mr. Mustafa to come on stage to collect the certificate? Thank you so much, Professor Tabilshi. And with this, we end up our second day of our conference.
Yeah, please, tomorrow 9 a.m. we'll start with the 2 keynotes and 1 panel. So please be there at 9 a.m. tomorrow. Thank you so much.
Should I shut down?
Yes, please.
The system will be here.